Today I want to tell you about the results of a truly remarkable study that tells us a lot about how our future with artificial intelligence is going to look. Large language models fed with a body of existing scientific literature predicted with amazing accuracy the results of studies that they were not trained on. Yes, that's right, they knew the results of scientific studies without even doing them. Current AIs that are mostly large language models have a huge advantage over human scientists for a simple reason. They can read more of the scientific literature faster. This can make a big difference because the number of scientific publications is increasing exponentially, too fast for any human to follow. Indeed, the entire physics literature has doubled since I made my PhD. I believe that the rapid growth of scientific literature is one of the reasons why scientists specialize into niches, and it isn't helpful to knowledge discovery. It makes you suspect that scientists must have missed a lot of connections that are just there, waiting to be found. The idea that there is hidden knowledge in the scientific literature isn't new. Already in the 1980s, the computer scientist Dan Swanson had a clever idea. He studied the distribution of references in scientific papers and found that, on occasion, studies on two separate research topics would have few references between the two topics, but would refer to a common third topic. He speculated that this indicates so far unknown links between the separate research topics. And indeed, Swanson found a concrete example for this. In the 1980s, scientists knew that certain types of fish oils benefit blood vessels. They had also found in another line of research that patients with Raynaud's syndrome do better if their circulatory health improves. This led Swanson to conjecture that patients with Raynaud's syndrome could benefit from fish oil. In 1993, a clinical trial demonstrated that this hypothesis was correct. You may find this rather obvious, and I'd agree it's not a groundbreaking insight, but this isn't the point. The point is that the scientific community missed it. It was right there in front of their eyes, but no one noticed. That was in the 1980s, but scientists have built on this idea since with better analyses. A few years back, a group of researchers from California studied the material science literature with a simple neural network. They did not, like Swanson, look for relations between research studies by using citations, but they did a word analysis of paper abstracts. They found that a number of thermoelectric materials were associated with the word thermoelectric before anyone knew they were thermoelectric. The knowledge was in the word relations of the literature before any human noticed. They also used the existing literature to predict new thermoelectric materials. But that was before the new large language models were unleashed onto the world. And this new study is now testing out how much hidden knowledge we have in neurobiology. They trained several large language models, including OpenAI's GPT-4 and Meta's Llama 2, on more than 120,000 full-text articles from neuroscience journals published between 2002 and 2022. Then they recruited about 170 neuroscience experts and presented both the AIs and the human participants with two versions of a neuroscience abstract, one original and one altered with incorrect results, and asked them to identify the correct one. General-purpose LLMs like GPT-4 got it right in about 81% of cases, significantly outperforming human experts, who averaged about 63%. A fine-tuned model further improved the AI performance to almost 85% accuracy. The point of doing this is not to say that these 80% of studies are useless because we already knew the result. No, the point is that this sort of analysis could be very, very useful to identify what the most promising new studies are. There ought to be key questions that are likely to unlock further progress, and I believe that these and similar analyses will be able to identify them. I know that this all sounds somewhat lame, it's just some literature analysis, but I really believe that this can solve a big problem. It's because humans can't digest all this literature. They can't draw connections that would be relevant for further progress. I really think that funding agencies should use AI-powered analyses to identify what research to fund. About 10 years ago, I wrote a proposal for the European Research Council to do such an analysis with a somewhat more difficult technique than the one that was used for this study. My proposal was declined on the grounds that I don't know much about data analysis. Fair enough, but of course the reason I applied for funding was to hire someone who knows how to do this stuff. And since I didn't get the funding, it just wasn't done. But that's okay, because it won't be long and then an AI will do it on its own. I got a lot of questions about some recent headlines according to which the universe had a dark Big Bang, a second hidden origin that offers potential evidence for... Yes, for what, I wonder? I had a look. The universe expands, which means that if you go back in time, matter must have been denser. If you use Einstein's equations to calculate just how densely matter was packed, the density becomes infinite at a moment approximately 13.7 billion years ago. And yes, for anyone wondering, density becomes infinite is physicists' way of saying we have no idea what's going on here, but we have a name for it. It's what we call the Big Bang, the first moment of our universe according to Einstein's theory of general relativity. In the past decade or so, some science communicators have unfortunately begun using the word Big Bang for something else entirely, namely the creation of matter in the already existing universe. But in the currently used theories, these are two separate events. Physicists believe that at the beginning of time, at the creation of the universe, there was no matter in the universe. There was just energy in the form of a field called the inflaton field and its potential. This field eventually decays into matter, that's normal matter and dark matter. And this creation of matter has now also been referred to as the Big Bang. In the physics literature, the creation of matter is more technically referred to as reheating, like, a microwave oven does. Beep, beep, your cosmos is ready. I really wish that science communicators wouldn't conflate reheating with the Big Bang, because it causes no end of confusion. But here we are. The dark Big Bang now uses the word Big Bang to refer to the creation of matter, and the idea is that normal matter was created first and then dark matter later. It was created in a rather similar way from the decay of a new field, which they just call phi. I find this very disappointing. I mean, after dark Big Bang, you really expect something more intriguing, like universal essentia, or cosmic continuum, or maybe Tim. Yes, I really think they should have called it Tim. But what type of dark matter does Tim decay into? Here's where things get interesting, because so far physicists have almost always assumed, for no particular reason really, that dark matter doesn't just have mass and sits there and attracts other matter. They also assumed that it does something else, that it has a small probability to interact with normal matter. This is why physicists built all these detectors to look for dark matter particles. They didn't find anything, which they want you to believe is progress. But, well, judge for yourself. The issue is, there is no particular reason why dark matter needs to interact with normal matter other than by its gravitational pull. This possibility has become known as the nightmare scenario of gravitationally coupled dark matter. We talked about this in an earlier episode. The problem is that in this case, there is basically no way you can figure out what properties dark matter particles have. Also, we thought, because these physicists who work on the dark Big Bang say that even in the nightmare scenario, we'd still be able to measure the properties of the dark matter particles. It's because this second dark Big Bang, when dark matter was created, would have been a rather violent event, a first-order phase transition from Tim to dark matter. This creates bubbles of the new dark matter, very much like when you boil water. These bubbles then join to larger ones. The thing is that this is a quite abrupt process, and that creates gravitational waves, and these gravitational waves we might be able to measure. The general idea of the dark Big Bang was proposed already last year. In the new paper, they now calculate what are suitable ranges for the parameters of the model, like the details of the phase transition and the particles that it creates. You see here the white region is the range of parameters which is not yet ruled out. And you also see that you can rule out a bigger part with some upcoming gravitational wave experiments that are the green and yellow regions cutting out a piece of the white part. By the way, this video comes with a quiz that lets you check how much you remember. Well, the authors of these papers nicely follow the playbook of theoretical physics. First, you make up a new theory that's unnecessary to explain any existing observations. Then you fumble the details together so that it hasn't been ruled out already. Then you claim that something interesting can be measured with some upcoming experiment. But it won't be measured. How do I know this? Because this is the same strategy of theory development that the people in this research area have used for decades. It's never worked before and will never work. There are infinitely many of such mathematical ideas to guess from, so the probability of anyone being correct is 1 over infinity, which is 0. But this also means that there are infinitely many papers left to write, and I can make infinitely many more videos about them, so don't forget to subscribe. Solar flares are unnerving already, but a new study now found that our sun is probably capable of superflares that are vastly more powerful than any flares we've seen so far. How did they find out, and how much do we need to worry? Let's have a look. Solar flares are giant eruptions of plasma from the sun's surface that blast particles and radiation out into space. Sometimes Earth is in their way. The radiation and the particles then rain down on us and can cause satellite malfunctions as well as trouble with the electric grids. The biggest solar flare that we have on record was the 1859 Carrington event. Many people back then reported auroras over Europe and the United States and disruptions of telegraph systems. At the time of the Carrington event, 2 measurement stations in England were keeping track of the magnetic field on Earth. Those devices worked by pushing an inked pen around on paper, and during the peak of the storm, that pen just ran off the page. So no one really knows exactly how strong the Carrington event was, but it's been estimated to have had about 10 to the 32 ergs of energy. I have no idea what that means either, but in everyday units, that's roughly the energy of 100 billion Hiroshima nuclear bombs. The solar flare from May this year, which you may remember, has been estimated to have had about 1/10 of the energy of the Carrington event. A superflare now is at least 100 times stronger still than the Carrington event, so that's 10 trillion Hiroshima nuclear bombs and up. We don't have any records of these, so for this new study, the researchers set out to estimate the frequency of such superflares from looking at other stars like our sun. They used data from NASA's Kepler Space Telescope. The Kepler mission ran from 2009 to 2018 and broke ground with its discovery of exoplanet. But Kepler looked for exoplanets by the slight dimming that the planets would cause as they transit in front of a sun. So indirectly, Kepler collected a lot of data about other suns. For the new study now, the researchers looked at 56,000 stars similar to our own sun. They found almost 3,000 superflares in the observations, for which they estimate the size and frequency. They find that the relation between the energy and frequency is similar to that observed in our sun. It's a power law. The larger the flares, the fewer of them happen. But here's the kicker: the bigger flares are more frequent than expected. You see this summarized in this figure. You see the bold green line? That's the data from the sun. It just stops at some highest value. That's the Carrington event, because we have no records of bigger flares. This dashed green line is the power law that fits this. This is how scientists previously expected the frequency and energy to be related. This orange curve here, that's the new data. You can see that this exceeds the expectation. They estimate the frequency of superflares to be 1 in a century. There's one caveat that I must mention here, which is that solar flares are usually a combination of radiation and particles from a coronal mass ejection. The particles are the more dangerous part, but these observations of stars only tell you the radiation. So what does this mean? There are two possibilities. One is that our sun is, for unknown reasons, much more well-behaved than the average star of this type. The other possibility is that we've been extremely lucky so far. Going by these observations, it certainly looks like stars of the same type as our sun can produce superflares. What'd happen if a superflare hit Earth? It'd be really bad news for Elon Musk, because chances are a lot of satellites will be damaged and possibly get out of control. So in the aftermath, we'd probably see space debris build up rapidly with the occasional chance of trash rain. That wouldn't be all of it. It's highly likely that a lot of old transformers would go boom, and we'd see blackouts all over the place. I don't even want to think about what might happen to supercomputer centers. Damages have been estimated to be trillions of dollars already for a Carrington-like event. And that doesn't account for the damage to living things. Earth's magnetic field can cope with a flare 100 times the Carrington event, but the larger the flare, the more of the stuff will get through and rain directly down on us. You know, I'd really like to know what the tail of this distribution looks like. Oh wait, maybe I don't want to know. At the very least, the auroras would be glorious. What if I told you that some problems in physics aren't just difficult to solve, they're unsolvable? Not because we lack the tools or intelligence or funding, but because they require calculations that are impossible, and provably so. This is exactly what a group of physicists just showed. Let's have a look. Physicists are fond of saying that ultimately everything is physics, because the behavior of subatomic particles gives rise to chemistry, which gives rise to biology, which gives rise to psychology and sociology. But what if, along the line, the one doesn't follow from the other? Then these disciplines would all be similarly fundamental, and physicists would have to stop being smug, which would be really unfortunate. This could happen because there are some numbers in mathematics that we know exist, but that we can't calculate. They're uncomputable. And what if somewhere in that relation between the small things and the large things, there are such uncomputable numbers? Then you could no longer make a prediction, because you can't predict something that you can't calculate. Well, at least you shouldn't. A new study now says that the behavior of macroscopic objects can indeed be impossible to calculate, but with some caveats. Their idea is based on the halting problem. That's the question of determining for an arbitrary computer program and its input whether the program will eventually halt or continue running forever. Alan Turing proved that there is no algorithm that can solve this problem for all possible programs. Answer the question for some programs, because you can just run them and see what will happen. Some of them will halt. For the others, you'll at least know that they don't halt within the time you observe them. But there is no way to generally answer the question for all possible programs. The halting problem is undecidable. The halting problem gives rise to an uncomputable number, Chaitin's constant, named after Gregory Chaitin. It encodes the probability that a randomly chosen algorithm halts, where the longer the algorithm, the less weight is given to its probability. These diminishing weights are there to avoid problems with infinity. But basically, to calculate Chaitin's constant, you need to know the probability that any algorithm halts, for which you need to know the solution to the halting problem, which you don't have. So, Chaitin's constant is uncomputable because the halting problem is undecidable. However, since you know that some algorithms halt and others don't within a finite time, you can approximate Chaitin's constant from below. If you were to wait for an infinite amount of time, then you'd get the constant precisely. So far, this is pure maths. But the authors of the new paper now use these properties of Chaitin's constant to construct a physical system that has uncomputable properties. They say, consider a lattice of particles that have quantum properties. The interactions between these particles, especially the strength of the interaction, can be controlled externally. This is something that physicists actually do in practice, usually with lasers. Yes, physicists really like lasers. What the authors of the paper do next is to construct an algorithm for a quantum computer that approximates Chaitin's constant. It's a quantum algorithm because the particles in the lattice also have quantum properties. Then they map this algorithm to the particles of the lattice. That is, they say they can engineer the lattice so that the interaction strength between the particles depends on Chaitin's constant. Next, they have an external control variable that could be, for example, a magnetic field. And depending on how this interaction strength of the particles in the lattice compares to the external control variable, the system is in one of two different states. The one has a gap in the energy levels of the system called the spectral gap. The other one doesn't. Don't worry if you don't know what that is. Could be a gap in the front teeth for all I can tell. It only matters that it's a measurable property. And it changes at a critical value of this control variable, which derives from Chaitin's constant, which is uncomputable. So if you change the control variable, you can't compute what happens. This is a truly profound result. It means that even if you know the rules governing the system at a microscopic level, you can't predict the behavior at a macroscopic level. The behavior of the system is in some sense unknowable. As they write in their paper, our result implies that no general algorithm exists to determine the phase diagrams, even under the promise that the phase diagram is exceedingly simple and illustrates how uncomputable numbers may manifest in physical systems. But if you look at their maths, then that's only the case if you run the calculation for the interaction strength forever and the lattice is infinitely large. I wouldn't exactly call that physically realistic. Indeed, this isn't the first time scientists have tried to construct an uncomputable physical property, and so far it's always required a system with infinitely many components. That makes me suspect that all these uncomputable properties only arise in some limit to infinity and therefore aren't physically real. So, plot twist, I think this result is evidence for the opposite of that claim. That said, I think this is a very interesting finding one way or another. Maybe one day we'll even find out whether the TikTok algorithm ever holds. Thanks for watching. See you tomorrow.